what else matters when it comes to spectroscopy? So on one hand, the issue of wavelength or frequency matters because depending on what you want to learn about something, you'll choose a particular wavelength and the instrument that uses that wavelength. The other thing that matters is when that frequency of electromagnetic radiation interacts with the matter, something else has to happen. And that's that energy gets transferred from the photon to the matter. Right? And this is kind of a very simple graphic, but it's a graphic that represents an instrument you guys used back in Gen Chem, the Spec 20. Sometimes I overgeneralize a Spec 20 as a glorified flashlight, because that's kind of what it is. You've got a light source, you put the sample in that cuvette, you stick it in the instrument, and on the other side of the cuvette is a detector of some sort that compares the amount of light that was coming through without the sample to the amount of light that comes through once the sample's been put in. And of course, if the sample's absorbing the light, the intensity of the light goes down. Why? Because energy's been transferred from the light to the sample. All right? And most of the techniques we use today are this type of spectroscopy. They're not all, but most of them are. IR and NMR both are. So we send the energy into the sample and the instrument reads it as a difference and data gets sent out from the instrument. All right? Pretty simple graphic, pretty simple concept. But those two things have to happen again. Wavelength has to match the properties of the compound you're looking at, and energy has to be absorbed. Here's why we use both forms of spectroscopy in organic chemistry and the emphasis of each of them, right? Infrared tells us about functional groups. This is why I sent that email yesterday that said, look in the inside cover of your textbook. There's a table of functional groups, and it's really a good idea to re-familiarize yourself with those functional groups, because that's what IR is about. All right? It tells you the functional group. If you wanted to know if a particular compound were an alcohol, grab an IR. Put a sample of the unknown compound into the IR, wait for it to do its thing, and then look for something in particular that's characteristic of an alcohol. And all alcohols will have the same characteristic peak in an IR spectrum. Now, can the IR tell you what alcohol it is? Maybe. All right? NMR. NMR has a different thing that it looks for, right? IR looks for functional groups. NMR tells you the most information about the carbon skeleton. All right? Tells you if you've got 4 CH2s, 1 CH, 2 CH3s. Right? That kind of information can come out of an NMR spectrum. It's wonderful. Can an NMR tell you that you're also looking at an alcohol? Yeah, pretty much. Okay? So there is some overlap between the two, but where each one has its strength is that IR tells you about functional groups, NMR tells you about connectivity, right? The number, connectivity, and the environment of carbon and hydrogen in a particular organic compound. Okay? Thoughts, comments, anything I need to say again? All right. Here's another table that gives relationships based on energy And now instead of talking about like size of the animal or things like that that it relates to, I want to look at what it corresponds to within a molecule. Okay? And these are, look, it's X-ray, UV vis, infrared, microwave, radio frequency. So what's happening there? Well, if you think fast back to that table, or a couple of you have the textbook, you can look at that other table. But realize, I'll tell you what the relationship is. Highest energy is at the top, X-ray. Lowest energy is at the bottom, radio frequency. And they are in order, going from top to bottom, as far as energy goes. And if they're in order as far as energy, they're also in order as far as frequency. Highest frequency at the top, lowest frequency at the bottom. And they're also in order as far as wavelength. That would just be the other way around. Longest wavelength at the bottom, shortest wavelength at the top. So, let's think about this for a moment. X-ray, very energetic frequency. Very energetic photons. Right? So, what can that high energy photon do? Well, it can get all the way down to the sigma bonds. It can knock electrons out of orbit. It can do all kinds of havoc to a molecule. That's why, and as you know, X-ray has its medical purposes, but that's why you don't have very many X-rays over the course of your life, and the people who actually work with X-ray instruments take precautions, hiding behind lead-lined walls, wearing lead-lined aprons and things like that. And even draping lead-lined aprons over you if you're getting an X-ray, so that the X-rays only go through the part of your body that they're most interested in seeing, right? Because they do damage. UV vis, not nearly as energetic. It can't get way down into the bottom energy wells of electrons and knock them out of orbit, but it can interact with the pi system, right? Remember, they're the electrons that are part of the double and triple bonds, right? So those electrons are the ones that get interacted with. They're at a higher energy level to start with, so they don't take nearly as much additional energy to get promoted to another orbit. Visible light operates in conjugated systems. Now, we haven't talked about conjugated systems in here yet. But to say it quickly, it's a double bond, single bond, double bond, single bond, double bond, single bond. It's that pattern within a molecule. Infrared, now put infrared in red because it's one of the topics of the course. The ones that are in black we don't deal with, other than noting their presence. Infrared, though, a lot less energy. In fact, now it's called vibrational energy. Here's the thing. The first three are all energetic enough that they're actually interacting with electrons. Infrared, though, interacts with the molecule. It's not energetic enough to get down and knock electrons around. What's vibrational energy? Well, we'll talk more about this in a few minutes, but just to say quickly, remember, molecules are always in motion. And one of the simple models that works for a chemical bond is that of a spring, right? Springs will go back and forth, they go sideways, they move. So the bottom line is, all the bonds in a molecule are doing that. They're going back and forth, they're going sideways, they're going back and forth in different patterns relative to each other. That's vibrational energy. The molecules have that all the time. Microwave energy, less energetic than infrared, interacts with rotational energy. So you can think about that just simply as molecules are doing this too. And microwave energy gets into that area. Radio frequency, even less energetic still. Nuclear spin is what it interacts with. Now that's a weird concept. Nuclear spin. To say it quickly, and we'll get back to this when we actually talk about NMR, remember your quantum numbers for electrons, right? One of them, the last one, m sub s, was plus minus 1/2, right? That's magnetic spin. Electrons do that, or electrons have that quantum property. The other subatomic particles have that same property. In fact, they have a similar address system in quantum mechanics to what electrons have, but we never really bothered talking about that. So protons and neutrons also have spin, plus and minus 1/2. Depending on how many neutrons and protons a particular nucleus has, gives that nucleus a net, either gives it a net spin or it doesn't. If it has a net spin, then radio frequencies will interact with it. If it lacks it, then they don't. But we'll talk about that. You can think about it loosely as a top spinning, but that's not really the best model, but it kind of works. All right, thoughts, comments, things